Shall I introduce
the
speaker? So it's my pleasure to welcome our speaker today, Dr. John McGregor, who is are you an emeritus fellow or an honorary?
They call it honorary fellow.
Honorary fellow of CSIRO, where he worked for many years after working at the Bureau of Meteorology, or was it something else?
A joint unit with the Bureau.
Yeah. So it's a bit separated from Melbourne. It's out in Aspendale, so on the coast, isn't it?
Yep.
Yeah. And he's going to talk about the efforts at CSIRO that he's been involved with for many years with the semi-Lagrangian model, working on various cubed grids. And is that all I need to say?
Yep.
Right. Off we go then.
Okay. Thank you very much, Jim. It's great to be back at NCEP again after at least 15 years or so. Last time I came, you were in a nice cube-shaped building, which inspired Misha to start his cube grid. Misha's not here yet.
Might be dialing in.
Dialing in, okay. So I've continued on with that. I did some advection type. Oh, actually, the next slide. If I can find. Are you moving it or am I moving it?
No, you can use
this one.
Yeah, it should work. This one.
This one.
Yeah.
Maybe.
It doesn't work. Yeah.
This one.
Yeah.
Which one was it?
To the left.
Left one. Okay. All right. So started working on advection problems back in about 1996, 97, and that's when actually I'll show the grids in a minute and come to that soon. But I have a reversible grid, which was finalised about 14 years ago now. We have many physics options. Have a coupled ocean added on the same grid, and it's highly vectorised. Cube geometry is quite convenient for running on massively parallel systems. And the original model was on the conformal cubic grid developed by Misha and Jim and Fedor. But there's also developed versions on the uniform Jacobian grid, and that one is this is semi-Lagrangian like the one on the conformal cubic grid, but this is a split explicit version in flux form, and we mainly use the model for specialised NWP and climate downscaling. The Bureau of Meteorology, they've strangely adopted the UK model for their forecast model, but we are still busy with our own applications and development. Okay, so I'll show the various grids. Back in 1972, Sidorni proposed a mnemonic grid where you take a cube, draw a regular set of X and Y grid lines on the faces, and then project towards the centre of the sphere, or have it inside the sphere and project outwards. It's equivalent. Most people these days, when they use a cubed sphere grid, use this modified one, which is the same grid there, but you subtend equal angles at the centre of the Earth, so as to make it equiangular. So this one gets rather crowded at the panel edges because they're further away, but you can compensate for that by making angles equal at the centre of the sphere. These ones, the grid lines are not orthogonal, and you get a change in direction at the edges of the panel. The new model here, and many other cube sphere models, use this grid. The FP3 is what yours is called now, isn't it?
Yeah, it doesn't use exactly that grid. It uses something in between those two.
Does it? Okay.
Where the grid points are uniformly spaced along the edges of the cube.
Okay.
Halfway in between.
Okay, I'll have to check into that later. So what we've been doing is the conformal cubic grid proposed by Michel and Jim and Fedor way back in about 1996. I was at a conference in Montreal talking about my advection work, and Jim revealed the existence of this grid, which seemed a very good idea. Everything's orthogonal and equations are much the same as lambda conformal, which I had been using with a limited area model, or locator projection, very similar, just change the map factor. So that's what we've been doing for a long time, and that works very well. And I'll say some more about that. But a few years ago, Jim told me there was the uniform Jacobian version of that. So that's derived from the conformal cubic grid, but by some variational methods. Jim and Misha managed to make the grid cells all have equal area, and that's rather nice. So the grid lines are not orthogonal, somewhat like the other grids over here, but there is the lines smoothly progress from one panel to the next. And the newer versions of the model are on that grid.
So the top two panel and compared to the bottom right one, I mean, I can visually see that along the lines, along the edges of these things, there are like blemishes or something. Similarly, on the second, on the right top, they also like a convergence of the thing. Whereas the rightmost one, the EJ, seems to be kind of quite uniform, very nicely.
Here. Completely uniform.
Yeah, right.
That's right. It's very, very nice. So if you're using a cube-based grid, I think you should be using that grid while you're at it. It's no more complicated and has these extra advantages because it very smoothly over the edges. You avoid any grid imprinting. So with these grids, if you look closely enough, you'll usually see some grid imprinting. The same grids, just looking at the vertices. This shows the equal area. This gets somewhat crowded at the vertices, which means you need to use a semi-Lagrangian method, otherwise you have a time step penalty. For this grid you can use semi-Lagrangian if you wish, or you can use a variety of other methods. And this, you can see the Sidorni grid also is getting more crowded at the vertex, as does the conformal cubic. So most of the time I've been working on the conformal cubic grid. It has reversible staggering, which I'll describe shortly. It has the Miller-White non-hydrostatic treatment, which Jim also suggested to me. And I'll show some comparisons of the Miller-White non-hydrostatic versus what MPAS have been doing to show that it does work very well and is extremely cheap.
So this conformal cubic now you're using is UJ, based on UJ or?
The one we normally use is the one in the top right corner. But the newer version, I'll also describe. Here you see it's more crowded. The newer version is the UJ, which works just as well, but I've still got a little bit to do. The stretch grid version I haven't got completely right, and input and output routines, but I'll show some comparisons later. So Jim suggested that too. We use the Schmidt transformation because we do a lot of regional climate modelling where we have to zoom down over a particular region. Semi-Lagrangian, that's needed because of the crowding near the vertices. Grid lines are orthogonal. Isotropic delta x equals delta y everywhere. Parallel I/O works very well. We have parallel I/O. If you're using MPR, you really want to do parallel I/O. I assume you're doing that here as well. and it scales well from many processes. This is an example of a CM86 grid showing every second point about 100 kilometres, so that's a typical sort of grid we use for test runs and AMIP style runs, that sort of thing. So the grid variables are all located at these points where the dots are: temperature, UV, surface pressure. So each grid cell is a quadrilateral, which is convenient. However, during the calculations we need the U values in east-west type direction and the V values in the north-south direction to be in an Arakawa C type configuration. And I have a reversible procedure I'll describe in a moment, where the U's and V's are transformed reversibly to those positions. And because it's reversible, it ends up with very good dispersion properties, essentially the same as the spectral method for atmospheric.
So where do you carry the coordinate vertical velocity, which is used for diffraction, for example? So where do you carry it? Is it kind of in like on the interface or something there, or is it also
the vertical
on the
velocity? It would be at the half vertical levels. The temperatures we're keeping on the Lorentz type grid, not the Charney-Phillips.
Okay, so Lorentz table for distribution.
Yeah. A lot of groups seem to use Charney-Phillips, but we're still like the Lorentz grid.
But the A grid is actually basically for the semi-Lagrangian benefit that you have, and you have this staggering business, right, which is helping with the.
The A grid is very convenient for the semi-Lagrangian because you only need the one set of departure points for everything. You don't need separate departure points for staggered U's and V's or anything like that. This reversible procedure does preserve two grid waves. If you have a two grid wave preserved, we don't mind that. So it ends up with lively winds, and the kinetic energy spectra turn out to be very good because of this reversible staggering technique. To show you how it works, we have, looking at the U component, these integer numbers are at the centre of the grid cells, and we want to go to the cross points at the halfway points, and so a pivot point is introduced 3/4 of the way along or 1/4 of the way along, and you can write the value at the pivot point as 3/4 of that one plus 1/4 of that one, or you can write it as 3/4 of this one plus 1/4 of that one. So that gives this set of equations. So if you know the staggered ones, you know for the non-staggered with this tridiagonal system, or the other way is also a tridiagonal system. So it's a cyclic tridiagonal system going around four panels of the cube, and similar for B, going 4 panels the other way. You can also do a higher order scheme with using three points, so this one can be that and that combined, or similar for the cross one. And that can be refined somewhat, as Jim again told me.
So the method, does it necessarily need to be global?
It's easiest if it's global. It would be nice to do with other things like vertical. In the vertical for temperatures, it would be nice to apply it to stagger the temperatures back and forth.
No, I'm actually talking about this one, that the staggering business that you're doing, that does it have to be cyclic in X, Y, and the other directions, or can it have a regional application of this breaking up the thing with some boundary conditions and stuff, right? So
you'd need to modify it somewhat. I've played around a little bit with that, but I haven't quite resolved how you do it. For example, an ocean model ideally you would build in the land boundaries, but you have more staggered points than unstaggered, or vice versa. So you have to do something about
you
that.
might have a null space. Going one way, you might have a null space. You have to be careful that you're not dividing by zero.
Yeah, you'd have to filter out one of the high wave numbers somehow. So I've spent a little bit of time playing with it, but I haven't quite worked out the best way. We do have an ocean version using this with my colleague Marcus set up, but he's spread the ocean over the land a bit and done some quick fixes to get around that. But ideally you should take account of the different number of staggered and non-staggered points. So Jim pointed out this round of one corner, which gives us very high accuracy, and can be cyclic tridiagonal, or I've been using an iterative that would converge quickly, and it gives very good dispersion properties. So this is Dave Randall type test, two-dimensional test for the linearized shallow water equations, and in the atmospheric case over here with the large radius of deformation, that's the continuous type solution you would like. The A grid gives this different character. This is an X direction, that's a Y direction. It's the wrong shape. Two good waves in the X direction occur here and in the Y direction here. But you see the B grid is not so suitable. The C grid is good, as is well known. The Z or Z grid of Randall is also good, much the same as C grid, and the same as the spectral model would have. And this reversible grid is also, you can't see the difference from the C grid or R grid. To go to the ocean, then it's a different story. The asymmetry, there's no symmetry shows up in the reversible grid, depending on whether your pivot point is to the left or the right. So we do something there to alternate the direction of, alternate the position of that pivot point from time to time to get rid of that asymmetry. So with this asymmetry dispute, alternating the direction each time step.
So I actually. Can you go back to the 1 second? Just one.
How do I go back? Can I go back?
Yeah.
So both in the because there are the two panels, one for the like radius of deformation thing comparison. So the right panel for the ocean cases which is applicable, which I didn't get, is that the reversible grid, is that as good as the
well, if you alternate, then this averages out to be the same as this one. If you take the average over several times, it ends up being like that. Whereas the C grid has the wrong sort of character. The B grid is what most ocean models use, being best of a bad bunch. AB. This is the one you would like here. So as long as you handle this alternating of pivot points in a suitable way, then you end up with this type of acceptable behaviour. Probably need to do a little bit more work on aspects of that. Oh, I've lost it again. Oh, that one. So this is the Connecticut energy spectrum with CPAN conformal cubic for various model resolutions, 750 kilometre down to 7 kilometres, and for comparison there's the MPAS with a 3 kilometre grid, and it's a comparable minus 5/3, you're cutting off at a reasonably similar place. this little kit here is just an artefact of the diagnostic routine. So, moving on to the other dynamics, I'm calling it CCAM E here, the equal area or uniform Jacobian grid. So the numerics are extremely similar, but on the UJ grid, the complication is that the velocity components you have to take account of covariant and contravariant wind components. But we do get uniform resolution. This one, keeping the semi-Lagrangian numerics, it was very easy to get that working. I was working with this grid. I was working on the split explicit one. Tackled that, and that's hard work getting that going. I thought I'll better get the semi-Lagrangian one going, and that got that working in a few days, I think. But the other one's much harder work.
The semi-Lagrangian that you have constructed, is that mass conserving or?
No, I'll mention later the mass fix aspect. The flux version, of course, is.
Yeah.
So the reversible staging works just as well for the covariant and contravariant components, because it varies smoothly over the edges of the panels. You can do that same reversible technique. The main thing that happens is we require a larger stencil for the Helmholtz equation. It's a 9-point formula instead of being able to use 5.1.
So your the momentum equations, are they in terms of the covariant winds or the contravariant winds? I mean, is that a relevant question? Even I'm not sure, because they're on the A grid, right? So.
That's right. It's there's some covariant, some contravariant in the equation.
But the UV momentum equations, they are on the staggered grid, right, or not? I mean, are they on the C grid? And
there's some tricks going between the staggered and non-staggered. I might have the equations at the end. I'm not sure.
So did you write something on that, like some notes or something, office notes?
Some notes are overdue. Yes, I'll do it very soon. There's some
in the works here.
Some tricks or some nice treatments you have to do to get that right. So multi-grid works very well for this larger stencil. And I'll also mention the CCAM treatments, neurorography, and the Miller-White non-hydrostatic, and that works automatically in this arrangement as well. Conservation you asked about. So this version is in advective form, so use a posteriori conservation for mass and moisture. It's a global scheme, and that simultaneously ensures non-negative values, and each time step there's a correction made to the changes which occur during the dynamics. So the loss of mass is just in the dynamics part of advection and geostrophic adjustment type processes. So the correction I do is proportional to the dynamics increment. A little enhancement is the sign of the correction depends on the sign of the increment, so that keeps the corrections a bit smaller by having that in there. So it's a very cheap scheme. It just works up these different components of the various changes and the increments, and then does this simple minimisation to end up with them being non-negative, at least moisture being non-negative, and the total equal being conserved. I do it level by level. Then I was talking to Michael D. around just a couple of weeks ago, and they've been doing it at the ECMWF for some of their applications, and he said what they do in the verticals, he's done some extra things there to improve the vertical behaviour. But Michael produced a paper a few years ago comparing a number of these global fixer schemes. This one's a lot cheaper than most of the others, and was performed similarly well to the better ones that he studied.
Have you looked into making more local changes for the aposta RA constellation? Because if something's going wrong in one part of the globe, the global correction method will blame all of the grid points all the way around.
It'll tend to, although I've done just proportional to where the biggest change is. There's a local effect here where the biggest effect that's occurring over Melbourne, the biggest change in the dynamics that's occurring over Melbourne.
But there may be lots of places on the globe where big changes are happening simultaneously.
Well, they'll all be changed more than when not much has been happening.
Something might be going. The cause of the imbalance of mass might be in one locality where you're then making spurious changes to every place where there's a lot going on.
So one can't tell where what has caused the main overall change or which location. But it's a nice, cheap, easy way, and the true mass flux form is. Everyone says how it must be better, but I'm not completely sure whether it's necessarily better to do the flux form or do some suitable global fixer. You can make your fixer.
If you've got a very high resolution, even the flux form will have an accumulation of round-off error. So that might need some correction from time to time.
Yep, that's a good point. I should keep an eye on the time. Oh, there it is. Okay. In the semi-Lagrangian method, there's an unusual sort of term. This is logarithm surface pressure, but there's an upstream. You need the upstream value of the surface pressure. So if you're near orography, you can get overshooting problems. You know your departure points, you have to do a bicubic interpolation similar, and that'll give overshooting in that term. But there is a way of avoiding that, and so I've introduced a variable that's log VS hat, which is the log of the surface pressure, but then there's a topography contribution, ZSD on RT. So this fellow behaves more or less like MSL pressure, log, which will vary quite smoothly even over terrain. So it's much better to do the bicubic interpolation on this variable rather than on that one. And so formally, we could write log of surface pressure upstream value is the upstream value on this one, which is calculated smoothly, and we need an upstream value of this topography term. Well, if we say that our topography is defined exactly by linear interpolation.
So does this kind of connect back to the orographic resonance and the corrections?
No, I don't think so. I don't think so, but I'm not completely sure about that. So this fellow is calculated exactly if we hypothesize that topography is varying everywhere bilinearly, and then we just have this smoothly varying one, and that works very nicely. And there's something similar for upstream value of temperature. There's something similar I do. It's not not quite as neat as this one, but it also helps the temperature in the semi-Lagrangian calculation. The non-hydrostatic equation, this is the Miller-White type treatment that Jim suggested to me some time ago. So this is the ordinary hydrostatic equation here. The Miller-White term involves this acceleration term of omega, and by doing a certain amount of linearizing some of the temperature terms, this can be calculated as an addition to the phi calculation. So phi is calculated normally as hydrostatic, then this term is calculated and the modified phi is calculated. So it ends up being a correction to the usual semi-Lagrangian Helmholtz equation. There's a modified set of eigenvalues which depends on these reference temperatures and other terms in this one. So there's zero cost in doing that because it's the same Helmholtz equation just with different eigenvalues.
So the hydrostatic equation in the hydrostatic relation in the non-hydrostatic model, that now that you are kind of adding that Miller-White term, really, right? So, but if you are looking, for example, the Laplace's generalization of hydrostatic pressure based by the vertical coordinate non-hydrostatic models, then the hydrostatic relation that you write is on the right hand side like a delta phi delta hydrostatic pressure equal minus of alpha, which is the specific volume, right? And so that's actually the total density, not hydrostatic density. And that rho is again P divided by RT, and P is the total pressure. So there should be some kind of like equivalence between these things. And is that the Miller-White paper is actually like kind of dated, right? And or is it more recent, really?
Oh no, it's a long time ago. It's 1986, I think. But it's you're taking a few shortcuts. There's various terms that are being linearized, and
so but you still have your thermodynamic equation is still in terms of temperature, is it or not? In this non-hydrostatic model, or the hydrostatic model, your temperature equation is in terms of the temperature, not potential temperature, right?
Yeah, temperature.
So in that case, when you write that, it's like ddt total time derivative of temperature, and then you'll have the so-called omega alpha term, right? Mm-hmm. The classic this thing plus omega alpha. Omega is ddt of p, right? Now the subtle difference is that ddt of p in case of non-hydrostatic model be the true pressure, as opposed to the hydrostatic pressure, because hydrostatic pressure is determinable by diagnostic relations in hydrostatic model, really. Whereas now you have this ddt of total pressure, so you have to worry about that. So I just wonder how that is handled in this model. Yeah.
Well, in I guess this term here, the dominant. I'd have to check my linearization. I think the T here I'm just taking isothermal linearization for the T in this term, so there's not actually a total relief of temperature coming through.
I think the Miller-White, this thing is like a quasi non-hydrostatic approximations involved, but it serves the purpose, right? So,
well, I'll show some results, and it does better than I expected. So I'll come to that. So I did this one quite a long time ago, the 3D bubble. So this is a dense a bubble where the temperature is less than the environment. Theta is less than the environment. I'm doing this on a sphere, very very strongly stretched. I think its basic grid length was 200 kilometres per minute, stretched down to 500 metres over this inner panel for 35 levels. Extremely stretched. But the bubble, non-hydrostatic version, the temperature blob hits the surface and spreads out. The vertical velocities is downward here, upward there, and when it hits the surface you get these three rings spreading out, three vortex rings heading out from the middle, as you hope from other studies. Whereas the hydrostatic version, turning that off, it's not such a well-shaped bubble. It still hits the surface, but the vertical velocity is a bit messy. And you certainly don't get those nice rings spreading out. So
when you say non-hydrostatic, is that the Miller-White?
yes, middle
So
line.
it's really the quasi-non-hydrostatic.
Yes, quasi non-hydrostatic.
Have you done a fully non-hydrostatic simulation?
No, sorry. I've been quite happy with Miller White, so I haven't done
No, actually,
all that extra work.
it may not be that complicated because you have a good dynamical system, but you have to just augment that system of equations by the DT of P prime equation, really.
Okay.
And then it will kind of fit into with your temperature equation, really. So that's the only additional thing that you need. And the hydrostatic equation will still formally look like your model hydrostatic equation,
Yes.
but the geopotential will still be determined in the non-hydrostatic system by the same diagonal relation,
Okay.
but that density will be the total density. Okay, so that means if you complete the system nicely and you have a robust semi-Laplace and Lagrangian horizontal, it's
Well,
kind of a very
You'd have to solve that extra Helmholtz or Laplace equation as well. That's which is
and also how
expense,
your semi-implicit solver holds up in the non-hydrostatic system. That's also a very nice thing, really. So.
yes.
So in the quasi-non-hydrostatic system of the Miller-White type, am I right in assuming that you only have to solve one Helmholtz type equation?
That's right.
That's a clever trick then.
It's by a little bit of linearizing of those temperature terms in Miller White, they drop out, and it's just the omega which combines with the other omega type terms in the semi-implicit treatment.
So you do have a model decomposition in the vertical, like the hydrostatic model, still, right?
Yep.
Yeah, actually, that is that. Yeah, I think it is the right direction, really. That means you are retaining the advantage of the semi-implicit hydrostatic system in the non-hydrostatic model, and still have a stable system. Yeah.
Is it stable for the gravity waves as well?
Gravity waves guaranteed, but the sound waves, whether they are being killed a little bit, in the vertical or something like that. At the end of the day, it will be like whether the compressibility of the model has been compromised or reduced. That's the question, really, because the sound waves nobody cares, but the compressibility would probably has been affected or not.
And you must get some beneficial effects from that little epsilon, the forward biasing with your time stepping.
Oh yeah, down centering thing that you have.
The time centering you have to pay some attention to. That's true. With this non-hydrostatic term, you've got to bias it a little bit towards more implicit than explicit.
And also that I think the if we look at the bottom part where the rotors are forming and stuff, that will be the more interesting thing to show, because then you get more mileage out of these things. So we can zoom into the lower part near the surface there, and you can see the things kind of yeah.
Well, I'll show another example. This one I've run more recently. Some people like to run on a reduced sphere, so instead of the full globe, this one is reducing the radius of the Earth by a factor of 166. So it's an Earth which has got 38 kilometre radius, and this is comparing with the 2D ridge test of Shah and Klemp et al. Did this tested MPAS on this problem, and so this is the same configuration they used for MPAS. So theirs is a height Z-based vertical coordinate, whereas this is a sigma pressure coordinate, but that doesn't seem to make too much difference. So the ridge is 250 millimetres, 250 metres at the equator, solid body flow, 20 metres per second at the equator, isothermal. And this is showing the vertical velocities. So this is from the Klemp paper. So here's it's a complicated ridge. It's not just one thing. It's got a couple of bumps, and there's the vertical velocities where red is positive, red will be downwards, I think, and blue upwards. So the runs with this Miller White, they look rather similar. Adjusting the vertical coordinate to be for display purposes to be similar. There's the region that's looking. I was surprised how similar they look, and also adjusting the scale. This is This is in metres per second, and this is adjusting this to also be metres per second. So the magnitudes are very similar, and qualitatively looks good. So that's 35 level, and that's at 52 level. So I'll.
So this small planet, is that on the UJ or not really? Have you tried that, doing the small planet thingy? This particular experiment on the UJ global?
It'll work exactly the same, I'm sure.
So that means you can actually check the grid signature and stuff like that on the UJ, how significantly it's reduced.
This is where the ridge is in the centre of a panel, so it won't matter whether it's conformal cubic.
No, actually, I'm saying that what if you wanted to see that the grid signature is how significantly reduced in case of the equal area, this thing in a zone.
Actually, I have done that. I'm going to show that in a moment. I forgot I was about to show it. So there is a problem at the vertices. This is solid body rotation, this test. So there should be no vertical velocity initially except near the ridge. But here we have there's a vertex, there's one panel here, another one here. And there is this spurious vertical velocity near the ridge, near the vertex, I should say. So there should be 0 initial omega, some spurious omegas. We don't see it for...
So the vertical velocity is omega or is it W? Because this is the non-hydrostatic ground, right? So
I'm calling it omega. This is actually omega here.
Okay.
This is a mid-level value of omega, around 500 millibars. So it should be 0. So this odd pattern here migrates is affected with the solid body flow in the direction you expect, and does die away. So magnitude here is 65, drops down to 30 or so down to here. So it does dissipate, and it's only apparent for runs with very small grid lengths. And this is 600 metres. We've been having some funny effects with runs at 200 metre resolution, which we've tried to do some sailing forecasts. So it turns out to be related to the reversible staggering, and it's like an initialisation shock of that reversible staggering, getting the system used to the idea of having a reversible staggering going on. So I'm seeing if I can do some modifications to that to improve the problem. However, if you do a uniform Jacobian run, you still see some noise here, but it's 100 times smaller. So it's no longer an urgent problem. This is these are quite tiny. These ones are getting to be a bit of a nuisance, but uniform Jacobian gets rid of it.
So it doesn't really like very tiny grid cells when you have curvature as well.
It's because the grid size, you've got this very strong curvature as the changing by 120 degrees, and over. If you look at the size of the grid cell, it's Gauss's theorem or one of those suggests it's going to be more of a problem at those tiny grid sizes. But uniform Jacobian solves all that as well. So this version, it's the same computational efficiency as formal cubic, includes all the same features, and just doing a little bit on the stretch grid version. And we have a collaboration with South Africa for CNIP 6 with Francois Engelbrecht, and this is the dynamic core for the atmospheric part of that. So that's almost ready to do the real runs. We hope. I could mention that advection actually invent the 3D Cartesian ring components. So you've got U and D on the surface of the sphere, but you can break that down into a Cartesian equivalent with velocity along the axis of the Earth and the two others.
So that's still a two-dimensional wind, but you're breaking it down into
That's right.
components. So you still have an extra vertical component.
Yeah, this is ignoring nothing to do with omega. This is just those components on the surface of the globe. It helps to do it. It's easier to do it with 3D calculation, and then there's no discontinuities across panels or changing X and Y directions on the panels. Those behave very nicely. So semi-Lagrangian, it's all continuous. I told you about the surface pressure advection, and surface and temperature advection is a similar treatment. The flux, I have to finish at 2, do I? Or?
Yeah.
I better hurry up, or perhaps I won't worry so much about this. The flux conserving form still uses the reversible staggering, forward-backward split explicit solver for gravity waves, so no Helmont solver. The equations are a little more complete. There's no linearizing assumptions that you have in the semi-Lagrangian version, and it should avoid any semi-Lagrangian resonance issues, though I don't really see any of those, so they don't seem to be such a problem as expected. TBD for the advection should preserve some sharp gradients, which should have some benefits. Dynamics is somewhat similar to FV3 in some aspects, but we have the reversible staggering here. It's just showing the advection fluxes at the edge. You have a low order and a high order flux and super B limiter to combine them, following the Lebesgue method basically. Just an example, advecting a cone around the globe. This is the TVD version, and it should start here and it should come back to the same. This is a prism unit value 10, also goes around. But the semi-Lagrangian is it's not too bad. The TVD is supposed to be rather better, but it's.
So is this equal area grid distinct from the uniform Jacobian grid?
The same thing. Sorry.
Same thing. Yes.
Yeah, sorry, I just switched between what I call it. Yeah, uniform Jacobian, that's right. Pressure gradients in the split explicit one. I'm doing the was it Kurihara treatment a long time ago. You can calculate up the columns and work out the pressure or height on work out the height on those constant pressure surfaces. Because it's a vertical calculation, it does not penalise your MPI performance, and that seems to. I found that helps near mountains. So that's. Originally, I coded on the equiangular grid. It was very hard to avoid grid imprinting. So settle on the UJ grid, that avoids all of those problems. I am needing some small divergence damping at upper levels. I'd like to get rid of that, but we don't need anything like that in CCAM, the semi-Lagrangian ones, but we do need to put in this one.
So this model that the CCAMF, is that semi-implicit or is that split explicit?
It says it's split explicit. Somewhat similar to FV3 being split explicit. A little bit slower than CCAM. I thought it might be faster. Non-hydrostatic we can't use that Miller White easily because we don't have a Helmholtz equation there to piggyback on. So probably need Laprise type method with horizontally explicit, vertically implicit. Don't use this very better. I'll press on, I think. Some examples of precipitation, climatology. There's just a 5-year run. There's TWIM. If we look at the Asian monsoon, we see India high rainfall along the Western Ghats and the northeast part. SECAM, we're getting the Western Ghats and that type of rainfall. Fairly similar for the SECAM-E, and also fairly similar for the split explicit version. But I think overall the semi-Lagrangian ones are getting a bit better rainfall at the moment for some reason. But you do see some, over the Himalayas, you do see some spurious rainfall, I think, in the semi-Lagrangian ones, which seems much reduced in the flux form split explicit. Possibly because of that treatment of the pressure gradient term being able to go up those columns and do the more accurate horizontal gradient calculations.
That's the Kuriharas, this thing that you're talking about, right?
Yes. I believe that is helping the pressure gradient calculation. That's the same sort of thing globally. In case you want to see what's going on over the US, somewhere here. But, I better keep going. Wave behaviour seems quite good with our convection scheme. We're getting the MJO signal down in this area, and the other way is looking quite reasonable. And most of our work uses a stretched version, so here's a Schmidt transformation. So we take one of the panels and move it over a region of interest and then zoom down, so this is over the Vietnam region. And so this started as a 200 kilometre global grid and stretching it by a factor of 10 down to 20 kilometres over that region. And the far side of the globe will be 10 times coarser, 2,000 kilometres.
John, we have more than after 2 o'clock.
Oh, we're allowed to go on a little bit.
You
can go on till 2:30.
Oh.
People might want to get back to work.
Yeah, that's
okay.
other things.
I was thinking we were getting kicked out, but okay. Well, I haven't got much more to go, but okay, thanks. So a number of groups have used the Schmidt transformation for getting high resolution. We use it a lot. Limited area models, you've got that hard boundary which is a nuisance, so we don't have that lateral boundary and its problems here. You'll get some, I guess you get some refraction effects from waves going through the changing resolution, but it's somewhat minor. So when we do our downscaling climatrons, we typically downscale from a CMIP5 or CMIP6 run, where they've provided us with a set of SSTs. So we run it as an AMIP type experiment. But the CMIP models do have some errors in their present day SST climatology. So this was the CSIRO Mark III model, and this was January SST climatology, present day showing that there's errors of 2 degrees or so in many places. So if you drive your simulation directly with those SSTs, you'll get some biases just from that. So what we do is bias correct the CMIP runs, bias correct their SSTs. So we find the errors in the present day January or present day monthly SSTs, and you do that same correction for the whole duration of the run. So it might be a 200-year run. We apply that correction throughout, which is a fairly strong assumption, but it's hard to assume much else. We do also correct for the standard deviation of the GCM error type, which helps put the El Nino in the right place. So then we run a 100-kilometre, typically, CCAM run, driven by those bias-corrected SSTs, and then we downscale to 20-kilometre resolution, say. And that 100-kilometre run drives this run to some extent. It drives the coarser scales of this run. So we have a digital filter, so we calculate the coarser scale features of this run, and then the coarser scale features are applied to this run as a digital filter. So the fine detail evolves by itself, but the coarser detail is typically on scales greater than one panel. So length scales greater than that one panel come from that.
So you're not
100-kilometre
You're not
run.
exploiting the advantage of the Smith transform here that allows you to have an effectively regional model but with global extent.
Oh, we are. But
Because
we're applying the filter on top of it.
It looks like you're using two
There's
models.
a whole global run here, course on the other side and fine here, but the filter takes length scale, uses length scales greater than that, or it's a smoothly varied, it's not a sharp cut-off, but it's a...
Yeah. But you're still using this relatively uniform resolution model to drive it.
To drive the coarser features, yes, that's right.
Is that mostly just to keep the coarser features on the antipodal side of the globe under control?
We didn't originally do that, but you would find that the your fine resolution one would be somewhat different climate from the coarser resolution one, and then our impacts people found that difficult to deal with. They found it complicated to say how can a fine resolution one be somewhat different from the coarser one. So this way we maintain that consistency, and customers find it easier to deal with. Also, if you're very strongly stretched, you will get some artifacts of diffraction effects of waves and so forth, which will distort the
What I'm
climate.
wondering is, would you be better off just having a limited rectangle grid for this high resolution part and just drive it entirely around the boundaries as is conventionally done?
Well, you've got those edge effects then, but it's not much more expensive to run the whole global model than the limited area. We get speed up. The MPI works very well on this global system. If you start introducing special boundary regions, you've got all sorts of extra problems. It disrupts your MPI, I think. The digital filter, it's similar to a 2D collocation method or Fourier filtering, but by the cube geometry we can build arses along those around those sets of 4 panels. So it's a 1D, calculated as a 1D filter, or there's 3 sets of 1D filters, and if they're combined carefully, then it's extremely similar to using a full 2D collocation. So I've got a paper describing how that works. It's a little more complicated than the 1D, but it's combined in a tricky or an interesting way. My colleague Marcus found a better way to combine them.
But the grid is non-uniform, so you have to change the coefficients of the filter as you move around the globe, is that right? Or is it a constant coefficient filter? This is used in conjunction with the Schmidt transform.
I've just forgotten the details, but it does work out as an actual length scale rather than being in grid space.
But is it like a Shapiro filter, or is it?
Maybe. Sorry. I've forgotten the details of the Shapiro filter. But it's similar to in Fourier space, we're breaking down into wave numbers and just dealing with finer and coarser wave numbers. And Marcus, my colleague, has generated an ocean model on the same grid, and that's still needs a bit of development, but it's rather than doing extremely long runs of typical ocean models, he's chosen to use the digital filter to force that from the SSTs of the other one. So here's an example here. This is a stretched run globally. It's 50 kilometre resolution, but it's been stretched so as to give 10 kilometre resolution over the Sydney panel, and the SSTs are now just 3 hourly from the into SSTs, but only on a length scale of something like one panel or greater, and that does generate the East Australia current behaviour quite nicely. East Australia current runs down the east coast of Australia, so that was seems to be heading in the right direction, but it's still a little bit of work needed on that one. Oh, I've almost finished what I had. So we have a few collaborations, mostly in the Asian region or Southern Hemisphere. Our strongest collaboration is with South Africa, CSIR, with Francois Engelbrecht, and he's very busy getting ready for CMEP6. We have had a number of projects over Vietnam with the University of Hanoi, New Zealand. We do run these very high resolution sailing forecasts. John Bilger in New Zealand set up a company, and if you go out there wanting a sailing forecast, that may well be the one that pops up on your internet, predict wind. So that's using these CCAM ones at 1 kilometre resolution with this digital filter approach, coming down from I think probably 100 kilometre globally or 50 kilometre globally, working down to that 1 kilometre sailing forecast, and they work well. We've also done sailing forecasts for Australia for the Beijing Olympics, where we were very successful in sailing. The London Olympics, where we were very successful in sailing. Maybe the next Olympics. Indonesia, Philippines use it for a number of applications, and a little bit in Sri Lanka, and Nanjing University we're starting something there. So I think that's all my slides.
No, thank you. Any more questions?
Any question from the telephone?
So I have one. Do you feel that you might benefit from using a vertical height coordinate instead of a pressure-based coordinate now that you're in the non-hydrostatic regime?
I think for semi-Lagrange it probably doesn't work quite as easily.
Why not?
Terrain following, does it? No, maybe it does, okay. You can be terrain following in height as well, of course. It's not high on my priority of things to do next, but do you think that has advantage?
I'm just thinking in terms of the effect of orography. If you could use something like Fedor's shaved cells or something,
Oh, right.
you might be able to alleviate for all time the serious problems that orography sometimes presents.
I think shaved cells doesn't carry over easily to semi-Lagrangian, I don't think. You've got different number of levels above the mountains and out in the...
But at least the trajectory shouldn't pass through the mountains. It's lower boundary conditions. You should go from one grid point or grid cell to an interior.
Okay, I've been tempted to go down that path from time to time. So yeah, okay, I'll think about it again.
Okay. Well, John's going to be around here for a little while, so you'll be able to talk to him if you need to. But, if there are no more questions, let's just thank John one more time.
That's me.
Haven't seen you for ages.
Around that one.
6:30. Looking young, still with dark coloured hair.
Yeah, it's
See, I told you, you recognise